So today we'll start off with this transistor. So in the last unit we have understood the working principle of PN junction diode, right? So we had just one P-type material sandwiched with N-type material. Now we'll talk about two PN junctions. Basically, if we sandwich one P-type, two P-type materials in between N-type or two N-type material in between a P-type material, so what will happen? We'll see all this, and we already, you all have studied transistor, but let's have a look again, and let's proceed. So first of all, diode, as we understood, it was a kind of rectifying device, right? It behaves like a rectifier, so it is to allow current only in one direction, right? Now in case of a transistor, we'll see that it is capable of having current gain, voltage gain, and also power gain. So for that matter, we call diode as a passive device, whereas the transistor, it's an active device because it can basically amplify your signal. It has a gain factor, current or voltage, power gain. So in that sense, a transistor is an active device, okay, whether diode is a passive device. Now the basic transistors, they are basically three types, okay. Let me see the chat. Okay, so there are basically three types. So one is BJT, the bipolar junction transistor, the most simple one, and then most simple but most the basic one, and then we have MOSFET, right, metal oxide semiconductor field effect transistor, and before that we have JFET, junction field effect transistor. So these are the basic three types of different transistors, or different transistor we'll learn, okay. So let me go with the block diagram like we did for a PN junction diode. So for a transistor, we have basically three different regions, right? So we have, let me just separate them. So we have basically one, we called it as emitter, base, and collector. So we'll see why we call it as emitter or why it is base or the collector. The nomenclature will justify it, okay? So for a transistor, so let me draw one transistor. It's a PNP. Then the another equivalent of this is your NPN. So basically all the P and N, they interchange each other. So in this, we'll just continue with PNP type of transistor, and the NPN transistor works very much similar way, just electrons and hole, this carriers just changes, but their properties are equivalent, not say same, they're equivalent. So if you understand PNP transistor working principle, you can easily understood the NPN, okay. So this is a very typical two-dimensional block diagram of a PN junction, NPN transistor. So it has basically three terminals, right? Now, now three regions. So coming to the doping concentration. So we have learned in diode, right? So sometimes we make one side heavily doped to get abrupt junction, right? Or to get certain quality in the diode. Like if you want a first response diode, that time we make one side heavily doped, or other side we make metal junction. So for a transistor to work more efficiently, we'll see why we are doing it. So emitter junction will be heavily doped, okay. It's the most heavily doped out of these three regions. And then base junction is moderately doped, and the collector junction is the least doped, lightly doped. So if you write like with rho, so rho E is the doping concentration. I'm just writing one notation rho. So rho E will be the highest, and then base, and then the collector. This is how the doping concentration varies within these three different regions. Okay. Now coming to the symbol. So for a PNP transistor, the symbol is, you are already aware of it, but let's put it again. So how to remember? So PN, your emitter is, sorry, base is N. So the current always you should write P to N. The arrow you should write P to N. So okay, so let me draw. This is your collector, base, and this is the emitter. And always we put the arrow in emitter of the transistor. So this is basically symbol of a PNP transistor. And the NPN you can guess it, right? So it will be something like, so this is your collector, base, and emitter. This is for NPN. So you will never forget, you just see base is P and emitter is N, right? So the current direction is P to N. So the arrow will be always P to N. So this is how NPN we write. Okay, so this is the symbol of transistor. In circuit we represent, right? Now in a diode we had just two terminals, right? So we had draw a quick diode. So we had just P and N, we had two terminals, and we could play with two different biasing, right? Forward and reverse, right? Only two types of biasing. But in transistor now you have three terminals, 1, 2, and 3. So you can do some combination, right, within this three terminal, forward, reverse. You can have multiple types of biasing condition. And according to the biasing condition, we basically operate the transistor in different region. Like for a diode, we operated in active region or forward bias. Basically, the current passes through it. It's a on state, or in reverse bias, it's a cut-off state. But in case of a transistor, you will see as we learn further, it has three different regions. So one is your active region, cut-off region, and saturation region. So depending on the biasing conditions we have in between these among these three terminals, we'll have different kind of operating regions, right? Now, in a transistor, the transistor is a uh, voltage controlled current source. We'll see that. So we basically control the current within a transistor or the terminals of the transistor by controlling voltage. It's a voltage controlled current source or current device, you can call the transistor as. We'll see that part. So this is how transistor. Now the doping concentration I already told you. Yes. Now coming to the different biasing conditions. So first, the active biasing condition. If you go to active bias mode, you will appreciate it. First, just let me tell you. So the emitter junction. So we have here two junction, right? We call it as emitter junction. This emitter base junction. We simply call it as emitter junction because base is common in both. And base collector junction. So we simply call it as collector junction. Okay. So when I tell emitter junction, it means emitter base. So the emitter junction is forward biased. Okay. Or you can call it as, okay, full also you can call the emitter and base junction, they are basically forward biased. And the other so this is the one condition for active bias mode, and second condition is the base collector junction, base and collector junction, this is reverse biased. So we have basically in active bias, there are two different biasing conditions. So we have to make emitter base junction forward bias and base collector junction in reverse bias. And in this condition, fine. So one more thing, coming to the current in a transistor. So as you can see, transistor is a three-terminal device. Now, if you know the current in any of the two terminals, you can always calculate the other terminal current, right? By using Kirchhoff's current law, right? Like PN junction diode, it's always same, right? It says just two terminals. So whatever current flows through the P side, it has to pass through N side. But whereas in transistor, so all the three current, if you take the direction, it has to be zero. If you call it, if you think transistor is a junction, then the sum of all these three currents should be zero, right? Kirchhoff's current law. All of you studied. So this is, so in a transistor, basically there are two independent current. Now let's try to understand the band diagram or the carrier concentration, the field distribution in a PNP transistor. As we did for PN junction diode, you can easily understand it's just another mode junction, nothing more. So let me just try to draw it. You can also try drawing with me. Okay, you see your screen and draw it. So it's a good practice. Okay. Okay. Fine. So I'm just drawing a transistor first. Again, this is all schematic, right? So I'm drawing the base junction. You see, almost all are equal. But in practically, the base junction will be the most narrowest one, right? Most thinnest one. Collector will be the biggest size, and emitter is in between. But the base junction, okay. So when it came into this context, so let me tell you the base junction width. It depends on the mean free path of the carriers. So the base width has to be less than the free path of carrier. Otherwise, it will recombine. We'll talk about it. So let me just draw it for now. So we have P plus. Okay, let me keep it blank inside. P plus NP. Again, so you make a habit, like put always emitter on the left side. You can do it interchangeably, but in exam or interview time, you will have tough time to remember. So always try to draw the same way as we'll be doing in your exam. Then okay. So even if you forget, you can remember. You can tell. Okay, so P plus N P. So this is our emitter, base, and collector. Now coming to a thermal equilibrium condition, unbiased condition. So all the three terminals are grounded, right? Like as we did for a PN junction. Same thing. We have two PN junction basically back to back. So how will be the depletion region? So as you can see that P plus, so emitter is heavily doped. So for a heavily doped, the depletion width will be the narrowest, right? So let's say it's this width. Now N, so the base is slightly less doped, right? So the depletion width will be little bit more. And the collector is very lightly doped compared to all these two, so your depletion width will be the highest one, right? So this is how the perspective way of drawing it. Of course, they are not in scale. Okay, so let's draw it further. So we'll be doing it like we did for PN junction. Okay. 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 We'll draw this edge also. Hmm. Okay. Now let's see the doping profile. So how will be the doping profile or the our acceptors and donor ions? So how do you write it down? Donors and acceptors. So let's draw one line here. So for P side, it is our acceptor, right? So they will become negative ions. And for N side, they are basically donor ions, right? So they will be positive. Okay. And this is this area, right? And then similarly, we have for this junction also, right? This is the NP junction, so it's reverse. Oops. Right. And this side we will have. I could not draw it with the scale. So again, you have to remember, right? The area of this region should be equal to area of this region. Area of this rectangle should be equal to area of this rectangle. Right. So here your junction width or the depletion width is more, so the concentration will be less. This height will be less. So okay, so these are basically positive, and these charges are negative, right? These are negative. This is how the doping profile, how the acceptors and donors ions, their concentration varies. Now, what about the electric field? So let's draw the electric field now. So electric field in a PN junction. So it was something like this, right? We already drew it. We already know. And for an NP junction, it will be other side, right? So this is how the electric field varies, right? The electric field. And this is the concentration, doping profile, Na or Nd. Now let's draw the interesting part, that is your band diagram or the EK diagram we popularly call, right? So for EK diagram, so what we first do is, so again let me just clarify. So this region is our neutral region in the P plus, and in the base, let me put a color. So this part is neutral. For the base, this part is neutral, and for the collector, this part is neutral, right? Region. And these unshaded area, they are basically donors and acceptor atoms. They're sitting there, right? So let's start from this side, P plus side. So let's draw the first for P type. So we have conduction band, valence band. and the Fermi level it lies. Now see the P plus is P side, it is heavily doped, so Fermi level will be very close to the valence band. You have to differentiate little bit because we have another P type on the right side, right? The collector. So here the Fermi level is very close to your valence band. Now, as it is in thermal equilibrium and it's a unbiased, basically all the three terminals are grounded, so Fermi level will be again constant throughout the device, right? So we got a reference now for Fermi level. So this is the Fermi energy level. Now, what about the N type? So we have to now draw the N region. So let's draw the N region. N region, okay. So for N region, the Fermi level, I mean the conduction band will be near Fermi level, right? So it should be somewhere here. Let's imagine. And so again, the band gap is same. Then you can do the same gap, right? This gap, do the EG. So this EG will be again same here also. This will be same, right? So this is for the N region, and now for the another P side. So another P side, where will be the Fermi level? The valence band. So this side is little bit lightly doped, so we'll draw a little bit away from the Fermi level, this valence band. And then again we have the conduction band, right? Now we have to just, again, this part is we have to draw, join them. Right. So this is how the final EK diagram of an PNP transistor with no bias condition. All of you agree with this structure? It's nothing, it's a PN junction. If you can see two PN junction just back to back, right? So now we'll try to do it for a forward bias, active mode operation. In active mode, how will be this band structure? Okay, so we'll do it just below. No, just below you cannot do because we need to modify this, this depletion width. Because when you do a forward, see, collector and base junction will be forward biased. So this depletion width will be lower, and we'll do reverse bias for emitter collector junction, base collector junction. This junction will be reverse bias. So our depletion width will be more than this. So to do a fresh one. Comparatively, if you want to draw. Oh, it's a long transistor. It's not taking just one more time. Okay, so we have again these two are the metallurgical junction, right? Now this junction is now forward bias, the emitter base. So we'll draw it a little bit thinner, this depletion width. In practical, it should be thinner, right? Even much more thinner than this, but for drawing purpose, it's not in scale. And this junction is reverse bias, so depletion width will be very much higher, right? So again, this side is P plus NP emitter base collector. Okay. So shall I draw it in the class, or you will do it yourself? It will take little bit of time. What do you prefer? Shall I draw it here step by step and explain to you? I think let's draw it. Huh? It will take some time, but it's worth. You can draw it with me as I'm drawing it. It will be practice for you also. Because sometimes when you see the full picture in book, no, and you try to do it for your exam, you will not know where to start, where to end. Forgot my scale today. Okay. Okay. This should be enough, and the final edges. Okay. Okay. So if you try to do the biasing, so let's show the biasing here. So we are doing basically wipe off these names. You already remember, right? Just wipe off. Just for the just keep only P plus N and P. So first, this emitter and base junction is forward bias, right? So this will be positive, and base junction, right? So this is forward bias. Now this other junction, it has to be reverse bias. So N side has to be reverse bias, means inside has to be positive, right? So this potential we'll later on see. This is called our V. So how do you call this potential? V, and then this is your base collector. So VBC, and this is V emitter base, V EB. These are the two bias potential. So this configuration is common base, right? This is common base. As you can see, the base is common in both the arms, both the terminals. Basically, later on we'll see one side is we call is input terminal, other side is output terminal. So for time being, just two arms. So and the base is common in both sides, right? So it's a common base configuration. We are trying to draw the all this parameter. Okay, so let's draw it. So how will be the this what is this called? EK diagram. You know this other NA and ND you can do it for yourself, right? According to this. Okay, let's do it. So again, the width is smaller. It will be smaller. It is not in scale. Don't compare with the left image. Okay. And this will be very thin, right? Reduce bias. So they are all positive donor atoms. These are all negative acceptor atoms, right? And similar case for the electric field, if you want to draw. So in the forward bias condition, your electric field value will reduce, right? The built-in potential and the electric field value also it reduces. Then the unbiased one. Whereas in reverse bias condition, this electric field increases, right? Junction electric field. They are not in scale, but again. So let's draw the EK diagram now. So let's start with P side again. So we have EC, EV. Right, EC, EV, Fermi level. So for the near the neutral region, so this region basically I'm talking about this neutral region. So the Fermi level doesn't change even if you bias, right? So the Fermi level position is intact as it was in normal neutral or unbiased transistor. Now what will happen? Okay, let me show this full. What will happen to this Fermi level in the N region? It will go up or down. Can anyone respond to this? This Fermi level in the N region. See, this side is forward bias. This PN junction or the emitter base junction is forward bias. So the Fermi level will go up or down in
Will
forward
go
bias.
up, up.
It should go up, right? So how much it should go up? What will be the difference?
VEB. VEB.
Exactly. So let's say this is one and this potential difference. So this is in voltage in potential difference if you write. So Q into VEB. This difference basically. I'll just wipe off. We need to draw some more things, right? Okay. And now, okay, let's draw this part. So inside, so you draw the conduction band now. Conduction band will be near to the valence band. And again, EG is same, so you can draw this. Now, what will happen the Fermi level in this P region? It will go up or down. Comparing this Fermi level, the center Fermi level, this P region Fermi level, it should go up or down compared to this center Fermi level.
Sir,
It is
down.
reverse bias.
Down.
Hmm?
It will go down.
It will go down. Anyone else? Somebody see. This is P and N. Okay, remember this is P side, this is N side. Forward bias, Fermi level is going up. Now they are in reverse bias in the emitter, sorry, base collector junction is in reverse bias. But you see the position of N and P. Now they are changed. In this junction, P is in left, right is N. But in this junction, left is N, right is P. So tell it wisely.
Should
It
go
is
up.
even more higher, sir.
It should go up, right?
Yes, sir.
It is reverse bias and we interchange P and N. So it will again go up. How much it will go up? What will be the difference between this Fermi level, the Fermi level in N and this collector P? It's the biasing, again, this VVC, right? So now let's draw the P side. So again, so this side is lightly doped. Oh, not here. Sorry. So this is the depletion region. Okay, sorry. So see, I was drawing wrong. This region is still in depletion region. So Fermi level, we draw it only in the neutral region, right? This side Fermi level basically bends according to the electric field. So this is oops, the Fermi level, and this is P type. So our valence band is here, and the conduction band is somewhere here. You can join these junctions. Okay, this is more or less the this. Let me make it a little bit smooth. Okay. So this is how the PK diagram for forward bias, or not forward bias, it's in active mode for a common bias common base transistor, common base mode of operation basically. Okay. Now, now let's do some current calculation or current gain of the transistor. Okay. So again, when we talk about the current gain or the current in a transistor or any junction, we assume always that there is no generation and recombination in the depletion region, right? And if you consider this assumption, then let's try to find out how the current flows in a transistor. What happens? Like PN junction, we understood what happens in forward bias. Like the holes are getting injected from P side to N side, right? And in reverse bias, the thermally generated minority carriers basically they take part in conduction. So again, here we have two junctions. So first junction, this is forward bias, and the other one is reverse biased. So you can bring all those concepts and merge these two concepts. One is forward and reverse bias, and you can do it by yourself, the transistor current equation. Okay, before going there, let me show you a typical transistor. How does it look like? It's not just we write like a block PN and they're sandwiched. So practically, we made it like this. So we have basically P-type substrate, and then we have lightly doped this N region, basically this is the base, and we make heavily doped P-side emitter later on. And all this process, we have learned how the diode is made, right? PN junction diode. It's the same process. You mask it, do lithography, etch it, then inject. So first, the start with it will be just a P-type material, and then you make N-type, you make P-type, P+ type material by injecting ions or the dopant ions, and by doing selective masking. It's the same like PN junction diode, but here a bit complicated. Okay, so now let's go back to the current equation of a PN junction. Okay, so here I just took this figure from the book to understand better. I mean, make it easier. You can go faster. Okay. So what happened? Okay. So in a PN junction, in a transistor, so in active, let's talk about this active bias mode. So we have basically emitter junction and base junction, they are forward biased. Now in forward bias, what happens is you basically inject the holes from emitter to the base, right? The holes in the P side, so P side is heavily doped, so we have plenty number of holes in the emitter. Now you do a forward bias and you push all the hole, you inject all the hole into the base region. And you make the base region very thin, very thin, such a way that hole can easily travel through and enter the collector region. It should not get recombined with the electrons present in the base region. You have to minimize that. We'll see why we need to minimize certain parameters we need to optimize. But this is our final goal. We have to transport all the holes from the emitter into the collector. So for that purpose, you make the base thin so that the whatever the whole mean free path, right? You make it less than that. Then the hole can easily get into collector region. But some holes, they will recombine with the electrons present in the base. So they will contribute, or they will basically will lose some emitter current in the base terminal. And now if you apply Kirchhoff's current law, this IE plus IE should be equal to IB plus IC, right? If this is the current direction. Now, what about this IE? This emitter current, it constitute of two terms. So first one is the hole, whatever we are basically hole are getting injected from emitter to base. This is the majority part, and there is some electron which will also get injected from base to emitter because they are in forward bias. But in as the base area is very thin, the volume is less, so the number of electrons are less, then the number of electrons which are getting injected from base to emitter, it will be less. But there will be some amount of current flow because of this electron injection from base to emitter. So we are just talking about now this part, this junction alone, emitter and base junction, right? They are in forward bias. Now let's come to the other junction. So other junction, what will happen? Most of the holes, they will get into the collector region because base width is small and their mean free path is more than the base width, so they can easily get into collector. And now collector, it is already reverse biased. So reverse bias means this p side, it is connected relatively negative potential, right? This p side, so the hole will get through this terminal, right? They can drip through, the holes can drip through this collector region easily. And again, there will be some current component because of some electrons, the minority carrier electrons, because this junction is reverse bias. So some minority electrons, they will diffuse through collector to base region. So we'll have some current ICN. Okay. Now let's write down all this equation and try to understand how this. So we are already 420. Okay, almost. So let's derive it next class. We cannot complete it. If we start, it will take at least some 20 minutes to 30 minutes. Let's derive in the next class. So let's recap today's class, what we have learned. So we understood the transistor construction, their symbols, right? Their mode of operation, EK diagram, right? And now we are getting into all the current equations. So